Hello, everybody. I'm Sarit. I'm a researcher at the University of Kaiserslautern in Germany. For this presentation, I'm joined by my co-author, Millie from HKS Architects and the University of Houston in Texas. I'll be walking you through the first half of this presentation, after which Millie will take over. So the title of our presentation and that of our paper suggests that our research is on radiation modeling strategy with regards to vegetation in urban microclimate simulations. So the question arises as to why one would need to incorporate vegetation in an urban context. So it's a known fact that climate in urban areas is different from that in surrounding rural areas. And this phenomenon, which is referred to as the urban heat island effect, results in thermal discomfort in outdoor spaces and also an increased HVAC load in buildings. So for the past 3 decades, there have been empirical and anecdotal evidence that suggests that vegetation can be a means to mitigate the effect of urban heat island, at least to a certain extent. Additionally, planting vegetation, which is also referred to as urban greening, is a means to improve the aesthetics of urban spaces. So there are several factors that one needs to consider when implementing any urban greening strategy. You can see some of those factors listed on the screen. Within these factors, there are some where human intervention is possible, specifically with regards to irrigation and soil composition. So for example, if the rainfall is less, we can always augment that with more water. However, for certain factors like radiation and wind, we can only anticipate, and this is based on historical data. So since in our research, we are interested in studying the radiation aspect of this, we began by reviewing the current practices of forecasting and communicating radiation data. So initial part of the research that we did was basically a literature review of studies from botanical and agricultural sciences. And these studies are cited in our paper. So what we found was that there is an extensive scientific consensus around the concept of daily light integral, or DLI, as a means of quantifying radiation for plant growth. Now, DLI is an aggregate of photosynthetically active radiation, or PAR, and PAR is a range of wavelengths of solar radiation that is responsible for photosynthesis. So PAR and therefore DLI depends on the spectrum of a light source. So if the light source is artificial, then the DLI value will almost be constant because the spectrum isn't changing. But as you see from the image on the left, the spectrum of daylight depends on the color temperature, and the color temperature of daylight would vary as per the season and region where it's being measured and where it's being collected. So researchers who've been working primarily in agricultural sciences have performed several macro studies in the past decade to provide DLI maps for entire countries. And you can see two of them listed on your screen. So these studies relate to the mainlands of United States and China. And in these studies, global radiation data was aggregated and then averaged into monthly estimates and then plotted onto maps. Now, the intent here was to provide region and climate specific guidance for selecting vegetation. So one of the questions in front of us was if these estimates could be relied upon to inform vegetation strategies at the city neighborhood level or not. And as you can see from the screen, when we try to use those maps to inform the radiation levels or the DLI levels at an urban scale, it doesn't quite work out. As you can see from the green circle on the right, if we plot the data from the DLI map, what we get is just a single value. And this single value by itself is not cognizant of the effect of topology, shadowing, or reflected radiation, which is brought about by buildings and man-made structures. So this brings us to the principal goals of our research. We were interested in formulating a strategy for providing DLI estimates for urban contexts in a way that would be compatible with the current practices that exist in plant sciences. And we were interested in proposing an annual simulation method, which in turn would allow us to create DLI maps for, in this case, urban contexts instead of entire countries. And to achieve this, we chose to work with accessible climate data sets and build upon the current state of the art in estimating solar radiation. So as you can see from the image on the extreme right, in a nutshell, what we were interested in was calculating DLI in an urban context. And this would require us to have an hourly annual estimate of radiation. And to do this, we drew upon the concept of daylight coefficients, which is used to calculate visible radiation or illuminance. And this has its background in building simulations. So the current methodology which is followed for daylight coefficients has its basis in the research that was conducted by John Mardevik and Christoph Reinhardt around 2 decades ago. And their methodology in turn is based on the idea of climate-based sky models, which was proposed by Richard Perez, and the sky discretization scheme, which was proposed by Peter Tregenza in the early 1980s. So the daylight coefficient method by itself, even when it's applied in an urban context, can only provide us with outdoor illuminance values. So now my co-author Millie will take over and explain how we got from this point to the calculation of DLIs.
Yes, so we can see here a simplified roadmap of this conversion, essentially converting the geometry and the climate data, which are inputs for our simulation, to DLI maps. This begins with a kind of typical radiance-based annual daylight simulation that produces an illuminance map, which then is converted to DLI. The conversion part can essentially happen in two different ways. One can be more precise, calculating PAR and relying on spectral measurements. And then that will be spectrally weighted to the specific spectra data of the specific plants. As an alternative way, which may be a little less precise, but a lot more practical and a lot easier to generalize, would rely on the use of conversion factors to compute PAR from visible radiation. And this is the one essentially we chose. Besides the methodology of using ready statistical TMY weather data, giving an emphasis to granularity of the spectra of the plants is not likely to yield meaningful results. So putting this approach into practice, we chose a site, downtown Dallas in Texas, for our prototypical study, which is an area with a subtropical climate that has been historically prone to the effects of urban heat island effect. And this can be verified in 3 dependent studies in the past 2 decades that are documented. And you can find those in our literature list. We also believe that the specific location we chose is a credible representation of modern urban neighborhoods in general, in the sense that the topology is comprised of high-rise buildings, roads, etc., in general formations that result in sufficient variability, very different from the traditional DLI mapping we saw in previous studies that make the assumption of the landscape being flat. So a high-level overview of the simulation methodology would be to take the chosen urban geometry, recreate it in Rhino, which is a 3D modeling software, and implement the daylight coefficient method by converting it to a compatible format for radiation modeling with radiance. So simulations were performed with a combination of existing tools and custom scripts. For the illuminance mapping part, we use Ladybug and Honeybee, which is Grasshopper plugins, and they use Honeybee uses DaySim for the generation of annual sky models, and some subsequent ray tracing calculations in order to generate those annual hourly estimates of visible radiation. Now, the conversion to monthly DLI estimates from the visible radiation to DLI was accomplished through custom grasshopper routines. Now, how can this inform the selection of plants? So typically in urban areas, urban greening strategies consider trees, food crops, or grass. So based on that urban context considered for this case study, we chose to evaluate 2 species of turf grass that are conducive to the climate of Dallas. So the evaluation was done separate for open spaces in the ground level and on the rooftops of the buildings. We can see here there is certain times during the year in winter that the growth of such species is prohibited by the available amount of solar radiation. Those monthly maps allowed these correlations. Through this study, essentially, we proposed an approach for urban radiation modeling to inform vegetation and vegetation selection, and demonstrated this approach through a case study. Presently, we are working on applying these insights gained from this research into thermal comfort simulations. So as a next step, we would like to build upon this research in order to create custom definitions of energy plus materials for grass types that can be incorporated into roofs of buildings. This is very much a work in progress right now, but the vision is to be able to create such materials that can be used both for energy building calculations, but also for outdoor thermal comfort estimates using Universal Thermal Climate Index. Now I would like to summarize our experience and provide a little bit of perspective for this study. And Sarith will talk to you through that.
So through this research, we were interested in proposing a more informed approach about selecting and incorporating vegetation in urban simulations. Now, as you can see from the points that are mentioned in this slide relating to challenges and limitations, these were mostly with regards to there being a lack of information, standards, and tools. In addition to that, as Millie was just describing the energy plus material, the current detailing that is possible for describing plants and energy simulations is not very comprehensive. So a part of our motivation in doing this entire research was to actually communicate these challenges as well, with the hope that anyone who takes up this research and tries to bring it forward would also be aware that these are some of the challenges that one might run into. Now, with that, I'd like to thank all of you for your time and attention. Please feel free to get in touch with us in case you have any questions or comments. Thank you.
Thank you.